All right, shall we start? Okay, this is the second part of the lecture, and then we'll continue the yesterday's talk.
Awesome. Alrighty, thank you all again for showing back up. It's nice to see that some people returned and weren't, intimidated or scared off by some anyway. So last time, roughly what we did is I defined what a celestial amplitude is via some Mellin transform of momentum space scattering amplitudes. And I'm going to review what we talked about in a moment. But before diving into this review, I just want to summarize kind of where we're going from here. So I've defined what a celestial amplitude is, but the next two lectures are going to be talking about certain properties of celestial holography that one can infer from relations in momentum space. So I'm going to be talking about very specific features that are particular to celestial conformal field theory that you might not expect in other conformal field theories. Okay, so these are particular to celestial holography. So today I'm going to be talking about a very special set of operators that appear in CCFT. And these operators tell you about conserved currents and conservation laws that scattering amplitudes enjoy. This is the story of asymptotic symmetries and so forth, which I'll get into by the end of today. And then tomorrow, what we're going to be talking about is OPEs. So with these two pieces of data in mind, the goal is that you'll be able to read most or all of the literature, really. You'll be quite caught up. Okay, so let me review what we discussed last time. We have this crucial equation that seems rather trivial, where we parameterize a massless momentum as follows. We write it in terms of this overall scale omega, and I'm going to define this p hat mu just in the following way. So a massless momentum is parameterized in terms of the variables omega, zz bar, in this sense. Okay. And p hat mu, which we'll see later today, is just some ease of notation. It's to summarize this four-component vector here. Okay. Now recall from last time that z and z bar tell us the location that a particle with this momentum exit on the celestial sphere. So somehow they're tied to the geometry. And the celestial sphere is it's a two-dimensional manifold, and this tells you like the location of the holograms. The celestial sphere is our holographic description. Okay. I also showed that the bulk Lorentz group acts as the boundary conformal group on the celestial sphere. So the 4D Lorentz group this gives you the 2D global conformal group on the celestial sphere. And today we'll see how this 2D global conformal group is extended to the local conformal group. Okay. The next thing we talked about is how conformal primary operators are defined from momentum eigenstates in the CCFT. So specifically, we have this crucial relation where we define a conformal primary of dimension delta by taking the Mellin transform of an annihilation operator of a massless particle in a momentum eigenstate. Okay? So I said that this conformal primary operator has dimension delta, and its spin is just equal to the helicity of this particle in the bulk. Okay? The final equation I wrote down yesterday is that the celestial amplitude, which is a function of these conformal dimensions, as well as these coordinates on the celestial sphere, this is just given by Mellin transforming all the external legs on a momentum space amplitude. So we have one Mellin transform for each external leg, which essentially replaces this omega parameter with the conformal dimension. Okay. And I'm going to write A tilde again here to be the celestial amplitude, whereas A without the tilde is the amplitude written in momentum space. Finally, we discussed the generalization to massive particles yesterday. So for massive particles, you're not integrating against this Mellon kernel, you're integrating against some other kernel which we described. And at the very end of yesterday, we did a very concrete kind of simple toy example of massless, and massive scattering. So 2 massless, 1 massive scattering. And we computed the celestial amplitude for kind of the simplest theory that one can imagine. Okay, let me now get into the new stuff. So the first thing I want to talk about today is going to be soft theorems. So for the next 20 minutes or so, everything I'm going to be talking about is going to be in momentum space. And then the plan is once we have these ideas in momentum space, we're going to be able to translate them over to the celestial CFT just using these kind of expressions that we defined yesterday. So let me give you some heuristic definition of what a soft theorem is. So they describe the behavior of a scattering amplitude when a massless, and this is crucial, they have to be massless, external leg has very low energy. So what is meant by has very low energy? Because energy is a dimension-full parameter. So it just means very low energy with respect to the other energy scales in the problem, the energy of the other particles that you're scattering. So roughly what this means is that you take this omega s parameter to 0, or more formally, omega s needs to be smaller than omega j, these other energy parameters for the other particles that appear in the scattering amplitude. Okay, so this is kind of the heuristic definition of what a soft theorem is. Let me summarize by giving a concrete example. So we're going to consider scalar QED. Now, the Lagrangian for scalar QED is pretty simple. The theory just contains a photon as well as a massless complex scalar. Okay, so these fields all have their canonical kinetic terms, and there's one interaction term in the Lagrangian, and this is given by the following. So A mu is the photon field, and J mu m, this is the matter current. So this m subscript is for matter. And for the scalar QED theory, we have J mu m is given by this simple form. So we have a charged scalar of charge q, and I'm going to write the scalar as phi. This is the complete Lagrangian description for a theory. Now I'm going to talk about what the soft photon theorem is in this theory. So the idea is that we have some scattering amplitude, which we don't know at this moment. And among the external particles is a photon. And the energy of that photon is ultimately going to be taken to be soft. So I'm going to write this is S for soft. And in addition to this soft photon, some other hard particles also appear among the external states in the scattering amplitude. So these straight lines are going to be for the charged scalars, and we'll say there are n charged scalars which appear in the scattering amplitude. And perhaps there are m additional photons which are hard, which appear in the scattering amplitude. So this is some very generic scattering amplitude, the most generic scattering amplitude that you can consider in this theory. It could have loops in it, take your pick. But ultimately what we want to do is study the limit in which omega s, this energy parameter for this one particular photon, is sent to 0. Okay? So I claim, and it shouldn't be too hard to see, that even without thinking about omega s goes to 0, this type of Feynman diagram generally decomposes into two separate pieces, the sum of 2 separate pieces. The first one is what happens when this will be soft photon couples to one of the external scalar legs. So you have all this same stuff, you have some stuff going on inside the scattering amplitude loops or whatever. However, the photon couples, to one of these external legs, so not to one of these internal propagators. Okay. And the second set of amplitudes that you need to consider is what happens when the photon couples to one of the internal propagators instead. So the photon just goes straight into the amplitude and it talks to something inside here. Okay. So this is a fair thing that you can do even when you're not working in the soft limit, but it'll be particularly helpful to study the soft limit. This is just kind of true by definition. Either this external photon, when it goes into the diagram, it talks immediately to one of these external legs, or it talks to one of the internal legs. That's kind of a vacuous statement. Not much is being said. All right. Now the actual physical content comes when you try and analyze what these Feynman diagrams look like in the soft limit. Okay. So let's study this first set of Feynman diagrams. Okay. The first contribution here can be found by looking at the interaction term between the photon and the charge scalar, as well as this propagator here. So the idea is that this Feynman diagram is equal to the Feynman diagram without this external line times some prefactor. Okay, so this Feynman diagram with this photon is equal to some prefactor times the Feynman diagram without the external photon. Now, how do you see this? Is because this here is literally this diagram. Okay, so to deduce the relationship among them, one just needs to find the interaction vertex and this photon, this propagator here. And I claim that everything that's going on inside is the same. So if you have some loops inside of one, then it's the same diagram appearing over here. Okay, so to find the relationship between these two amplitudes, you just need to evaluate the propagator and the vertex. And this isn't difficult at all. So the propagator is just given by the following. It's equal to minus I divided by PS plus PI squared, where PI is the momentum of this hard particle, this charged scalar. Okay, so this is the propagator here. This is just the usual results for a scalar propagator. And the interaction vertex can be inferred from this interaction term in the Lagrangian. So this isn't a hard thing to compute either. And at the end of the day, one finds that the vertex takes the following form. It's 2iq epsilon s dot pi, where epsilon s is the polarization tensor for the will-be soft photon. Okay, so photons are equipped with a polarization tensor. It tells you whether they have helicity plus or minus 1. And this is precisely that polarization tensor which appears in the scattering amplitude. Okay. Now, what we can do is we can expand this denominator, and we use the fact that everything that's appearing in our theory is massless. So we have PS squared is equal to 0, as well as PI squared is equal to 0. If PI was a massive scalar instead of a massless scalar, then you would have a minus m squared over here, or I guess a plus m squared, rather. And then you would have pi squared is equal to minus m squared. And what I'm going to say also follows for the case of a massive scalar. So the upshot when you expand this denominator is you find the following. The prefactor is equal to q times epsilon s, this polarization tensor, dotted with pi, the momentum of the hard particle, all divided by ps dotted with pi. Okay. However, when you're looking at all the Feynman diagrams that contribute to this process, the soft photon can couple to any one of the charged scalar legs. It can't couple to itself because this is an abelian theory. However, it can couple to these charged scalar legs. And so what we need to do is we need to sum over all these i's. So that's the contribution of this kind of scattering amplitude. It's just whatever's going on in here, I'm going to be totally agnostic to what this is, times this prefactor, which is just given in terms of the propagator and interaction vertex, which I've computed here. Okay. Now I want you to look at what's going on with this prefactor in this soft limit when omega s goes to 0. You see that there's a power of omega s in the denominator. So it turns out in this soft limit, this prefactor is actually singular, which may be a slightly weird thing from the perspective of scattering amplitudes. But Weinberg introduced this in the 60s, and I'll tell you a little bit more about the consequences of having a pole in energy in your scattering amplitude in a moment. By contrast, when you look at this kind of scattering amplitude, there will be no pole. Let me quickly summarize why. The reason there is a pole in this first set of scattering amplitudes is because this line here, this propagator here, actually goes on shell. And this is what I was saying before when you have a massive scalar. This line will go on shell whether your scalar is massive or massless. And in fact, this line going on shell is precisely what gives you the pole here. By contrast, this internal momentum will generally not be anywhere near on shell. So the reason this is on shell before is because this is exactly on shell, and you're adding a very small momentum to something that's on shell, so it's approximately on shell. Here, there's no sense in which this is going to be approximately on shell to begin with. So there's no sense in which you're going to get a pole here. And the upshot is this scattering amplitude scales like omega s to the power -1, and this scattering amplitude scales like omega s to the power 9. So when we're just focusing on the soft limit, only this kind of scattering amplitude is important. This scattering amplitude will give so-called subleading corrections, but I'm not going to worry about those for the moment. Okay. So with this in mind, I'm going to write the soft photon theorem for this particular theory.
In the end, the subleading is also some universal or is it?
Very good. Yeah, so very good. So it turns out that the subleading soft photon theorem is not universal. There's a few set of dimension 5 operators that you can add to the effective field theory. For example, something like phi f mu. Something like this could conceivably add it to the effective field theory, and this will modify the form of the subleading soft photon theorem. But this is actually being classified, so you know what kind of operators could modify the subleading soft photon theorem and precisely how they modify it. Okay. Anyway, we determine the following. Soft photon theorem, just in this one particular example. I haven't talked about universality or if this holds in generic theories with the U1 gauge boson. We've determined that this amplitude is equal to the sum over these prefactors plus some term which is finite as omega s goes to 0. And this all multiplies the scattering amplitude without the soft photon in its external states. Okay? So if you know what this scattering amplitude is, then you can infer what this scattering amplitude is, at least a leading order in this omega s goes to 0 expansion. Okay. So as Jungi was alluding to, it turns out that this soft photon theorem is actually completely universal. So previously I specified some Lagrangian, which is Yang-Mills and some charged scalar. You don't need to do this. It turns out for all theories with a U1 gauge boson, the soft photon theorem is going to look precisely like this, where the only modification is that Q gets a subscript I because various particles that appear in the external states can have different charges. Okay? So this holds for all theories of electromagnetism. Now, why is this universal? This is because 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 this is in any QFT, the photon, it always talks to charged matter through the matter currents. So for any U1 gauge theory, you can define the matter current as follows. This functional derivative of the matter part of the action. And because this structure is universal in QED, the fact that QED always talks to matter through an expression like this, Weinberg was able to find that this soft photon theorem is universal. So it's completely generic to all theories of QED. Great. All right. Next up, let me talk a little bit more about other soft theorems that will be helpful to us. So two of the other interesting soft theorems will be the soft gluon theorem and the soft graviton. And it turns out that these also have universal expressions, at least to leading order in the soft expansion. So for gluons, we have the following relationship. The n+1 particle scattering amplitude, where one of these particles is ultimately going to be taken to be soft, is related to the n particle scattering amplitude by this prefactor. Here, this TA are the generators of the Lie algebra acting on the ith particle. Okay, so we have some gluon with some color A. This is the color of our soft gluon. And this looks very similar to the electromagnetism case, except this U1 charge is just replaced by G Yang-Mills. Okay, great. And for the graviton, we actually know the leading soft theorem, which scales as omega s to the power -1, and we actually know the subleading soft theorem, and both of these expressions are universal. So in the gravity case, we have the n+1 particle scattering amplitude is given by root pi 8 g Newton times the following. So again, we have a sum because we're summing over all the external legs in the diagram. And the first non-universal fractions appear as sub-subleading order. So they behave as order omega s. And so they really do vanish identically in the soft one. Okay, so we can see here that this is the leading soft graviton theorem, and this expression is the subleading soft graviton theorem. Where this here, this J, is the angular momentum operator. Acting on the Jth particle in the scattering amplitude. And what I mean by this is that if the Jth particle is annihilated by annihilation operator AJ, then the commutator J mu nu is just determined by the Lorentz algebra. This is this minus 2i P mu partial P nu anti-symmetrized plus this spin term. So this is what we saw yesterday. So this is specifically what I mean. So it's important to note that when one's writing down soft theorems, these soft theorems aren't just kinematic factors always. They're not just numbers. So they're not just completely determined by kinematic data. Rather, they can be operators which act on the space of scattering amplitudes. So J is something that's not just a number in momentum space. So you can have these kind of objects also appear in soft theorems.
So this is for pure Yang-Milling gravity.
No, exactly. Yeah, so this is any theory with some gluons in it. You can have whatever matter you'd like, take your pick, and similarly with gravity. And again, these are universal just because gravity couples to matter through the stress energy tensor, and then gluons couple to matter through this non-abelian current.
For instance, the summation of I.
Mhm.
So in that case, all the legs set of this method. The key case, there's the sum is not for the photon lines.
Yeah.
But here, for the
Well,
lines.
I guess so. So I guess in this case, you can sum also over the photon lines, but the Q for the photon is 0. So formally, yeah. But the idea with soft theorems is indeed you do sum over all the lines. Okay. So a nice exercise, which again isn't a real exercise, but you know, something to get your mind jogging, is to compute this leading soft graviton theorem in your favorite model, just using this Feynman diagrammatic trick. Often in celestial holography, it's you know, you need soft theorems more than just these three to do various things that you're interested in. So having a concrete understanding of how to compute these things with Feynman diagrammatics is pretty helpful. Okay, the subleading soft graviton theorem, however, is not going to be a simple thing to compute. This I shouldn't assign as an exercise because Andy Strominger and Freddie Cacciezzo famously did this in 2016 or 2017. It's kind of a heroic paper. And here's their result, and they showed that this is indeed some universal expression. However, at higher order, again, there's some non-universal operators. These are dimension 7 operators that you can put in your effective Lagrangian, and one knows how they deform the soft theorem. But again, it's not a universal thing. It's not like all theories of gravity have the same thing going on at this order.
So it's been a while since I took a field theory class, but I thought the whole point of the soft theorem is that you have this divergence and it has to have this universal structure because then there are other diagrams where I have soft virtual loops.
That's right.
And it has to cancel.
Yeah.
Right. So I would think that so the statement is that there's something special about gravity that, however, do you know that, is there an analogous statement for the finite part of the soft virtual gravitons, so you know what the total answer is for the physical observable, or no, right? Because you haven't considered those diagrams yet.
That's right.
There's an analogous calculation one would do. This just tells you that there's a finite answer when I appropriately sum over kind of undetected soft photons or something,
Yeah.
right?
That's quite right. So I guess both leading and subleading soft graviton theorems are determined largely by general covariance and Lorentz invariance and things like this. So there's only so many things that you can actually put here. In fact, this was how the leading soft photon theorem was originally derived, this very simple case, where you need U1 gauge invariance and you need to be Lorentz covariant. And this is your option. You know, you don't have any choices. As far as your question about how soft theorems can cancel loop divergences and scattering amplitudes, which diverge in the soft limit, I don't know if there's a sense in which the finite parts are also supposed to cancel one another.
It's not about canceling, is it? Sorry. What I mean is that if I think about soft photon theorem and these iron divergences in QED,
yeah.
I see that I have exactly this. I have these other loop diagrams. They have to cancel. And when you do this appropriate kind of summing over external soft photons that you don't see, you get a finite differential cross section.
Yeah.
But it is something that you have to calculate, and it's not universal. It's theory dependent.
That's right. Yeah.
Should I think of this universal subleading part of the graviton somehow mean that if I do the analogous calculation for gravitons, I get something universal at leading order, or no?
That's a great question. I'm not totally sure. A lot of this question about canceling IR divergences that appear in loop diagrams, this is somehow regularization dependent. So it depends on choosing your IR cutoff to be somehow related to like the soft cutoff that you're doing here. So I wouldn't, I think there might be some like.
I mean, but it works, right? Like
That's right.
You do this calculation and you see that you agree with kind of QED experiments, right? So okay, we can't do these graviton scattering experiments, but I think about I think about physical observables, right? So my understanding of things like the soft theorem is that they're kind of a consequence of word identities.
Yeah.
But there's nothing physically observable in that divergence. You know that at the end of the day, when you calculate an honest observable, it disappears.
That's right, yeah.
Right.
That's quite right. Yeah, I don't know if these things are linked to one another at subleading order. Some loop IR divergences, some subleading subgrams. I'm not sure.
Divergence is not cancelable, then it's vector. In the case of gravity momentum conservation, and then the case of one.
I thought you have a soft virtual kind of leaping off of an external light and back onto it. It gives you an additional higher loop divergence, but you can isolate the divergence and it cancels against just throwing an additional soft filter or something. But it's been a while since I've taken a 3D class. So
No, that sounds right, but I don't know the details of like what RG prescription or what regularization prescription you use to regulate these. I wouldn't be surprised to see that subleading order, the IR divergences that appear in loops are somehow related to I guess this subleading soft graviton theorem.
is that subleading thing where the memory effect is, or no? Is that
Yeah, there's one memory effect for here and one for here. Yeah, good.
Here, the Stokes theorem looks like you need the masteries from particle. And here always related some AG and the charge, right?
Yeah.
Do you have like a Stokes color?
Yes, there have been soft scalar theorems. I think some of the first papers I've seen on this date back to maybe 2 years ago. And the upshot is for most of these theories, the leading soft scalar theorem will behave as order omega non. So it'll come in at this order. And then it's related to the geometry of the moduli space of scalar vacua. Yes, it's kind of.
What's the charge?
I guess the result is that if you have, well, maybe the simplest case is to think of some nonlinear sigma model. Okay, so you have scalar fields and some metric Gij on the moduli space of scalar fields. And then the upshot is that the n+1 particle amplitude, when you take the scalar I to be soft, is given by the covariant derivative with respect to I of the n particle amplitude, where the covariant derivative is meant to be taken with respect to the geometry on this moduli space where all the scalars have vevs. So you're slightly changing the vev of the scalar and you're computing the amplitude with these scalars have slightly changed vevs. I guess that's, yeah, cool. So a few years back, Strominger and others showed that these soft theorems and the corresponding soft modes, they actually act non-trivially on scribe plus minus, this conformal boundary that we were speaking of yesterday. And in fact, they're responsible for labeling infinitely many degenerate Minkowski vacua. And this is the whole topic of asymptotic symmetries, which I mentioned precipitated this idea of celestial holography back maybe 5 years ago. And in fact, we're going to talk about asymptotic symmetries later today, but we're going to talk about it from the perspective of the soft theorem, which is the maybe more modern perspective rather than the way this was historically developed. But we'll see the connection soon. Okay. Next up, I want to characterize maybe what I'll call some general theory of soft theorems, which aren't specific to gauge theory and gravity. Okay. So for a massless particle J, whose annihilation operator in momentum space is something like this, one may associate a soft theorem to it. Okay. So concretely, I want you to have in mind expressions of the following form. So you have some n+1 particle scattering amplitude with this particle I'll ultimately take to be soft and various other particles that appear. And this scattering amplitude is just equal to some soft factor acting on the n particle scattering amplitude, the one without this soft particle present. Okay. Now at tree level, you can do a series expansion in this small omega. So you can write Sj as follows. You sum over these k's, which are either integers or half integers, depending on the helicity of particle j. So if j is a boson, then you're summing over integers. If j is a fermion, you're summing over half integers. And you write this series expansion in the parameter omega k. Great. So I've written down this series expansion and I formally define the coefficients in this series expansion, S with this superscript K here. And this is just a totally formal manipulation that I'm free to do. And these are going to be called the soft theorems appearing at various orders in the soft expansion. So for example, if you look at the series expansion, there'll be a most singular term in the series expansion, the one that blows up most severely when you take omega S goes to 0. And this most singular term this is called the leading soft theorem. If you look at the second most singular term, this is called the subleading soft theorem. And so on. Okay, so you can look at sub-subleading soft theorems and something like this. And this is just a totally formal manipulation to define for you what we'll ultimately call the leading, subleading soft theorem and so on. Okay, so as I said before, these soft theorems, they're linear operators acting on the space of scattering amplitudes, which means again they can include things like J or the supercharged Q for supersymmetric theories. All these things are fair game. It's not just kinematic data. And at loop order, this whole characterization is corrected by terms that go as omega s to the power k log to the power L omega s. So they're corrected by logs at loop orders, these soft theorems. And there's been some recent papers where it seems like the power on the log is the number of loop orders that you're going to. Anyway, but this is still very much work in progress from the last like 2 months. Okay, so now we're finally, we finished talking about soft theorems. No, yeah.
Maybe what I meant is like counting the power of log and like has function. There should be relations between these things, right? You don't mean this, right? You mean nested logs.
No, I mean this. Yeah.
And that would include the nested logs. Log power, log omega power n would. If I have all the log omega power n, can I make log nested logs of omega? They don't ever come out.
I haven't seen any of this in those papers. Yeah, I've seen expressions like this though. They've only been able to do this up to, I think, 2 loop. So this is a little anecdotal. You know, the general theory is still kind of out on what happens at loop order.
Why are these called soft theorems? I mean, I thought the original theorem was that there's a universal thing for certain things, but this clearly, everything except the leading term, except maybe for gravity, is theory dependent, and so I don't understand the name.
This might just be a historical artifact. You could call it a soft theorem for a particular theory, or maybe you could just call it the soft operator associated to a particle in a particular theory. But I guess that might just be a nomenclature thing. This structure is preserved irrespective of the theory. The only thing that's theory dependent is what these soft operators actually are.
What is this statement about at loops? The leading soft theorem shouldn't get any loop corrections, right?
That's right. Yeah, that one's
worded
protected.
in anything. So these loops are only sub the first correction and so forth, right?
Yeah.
You can kind of non-perturbatively prove the leading soft theorem, I would think, for word identities.
Yeah, that's right. The leading soft theorem is protected, yeah, by word identities and things like this.
Yeah, so this Sj of Ps, this factor is exactly the factor which you wrote in those expressions.
Good, yeah, these are the Sj, this is like Sj for graviton.
Yeah, so how will you do the series expansion omega or those factors? It's just 1 by omega s.
Good, yeah, so this term here goes as omega s power -1, and so specifically s -1 graviton. That's a great question. This is good to motivate me to write this down. Now we have this p hat s, where I've stripped off the momentum, or this energy parameter omega s.
Yeah.
Okay, so this is how you can go from here to something that looks like this.
Then what is omega s to the power 0? Where does that come from?
That comes from here. So you see now there's 1 power of PS in the numerator and 1 in the denominator. That's good.
But that will not come in the gluon here. It will only come in the graviton now.
Yeah, so in the gluon, there will be some term here, but we don't know what it is. It's theory dependent. In the gravity case, it's fixed.
I just want to understand, in this gravity case, I have to assume I have minimal coupling, the loops change to this type of thing. How protected is this omega s to the 0 term there? If I have some non-trivial,
Yeah.
non-minimal dilettante-like coupling, do I no longer have that term, or is that really a universal spin-2 statement?
This one's universal, yeah.
So in this case, I don't get any log omegas, I only get omega log omega.
That's right. I mean, this hasn't been proved at the level of mathematical rigor. As I said, like, this is very new in the field. I think this paper only came out for 2-loop order maybe a few months ago. So don't be surprised if the state of the art changes, but that seems like the impression of everyone in the community.
Okay, so then just, what is the level at which this graviton theorem is proven?
Yes, yeah. This one was some maybe 2016 or 2017 paper. And they have all this complicated Feynman diagram beasts, and I think this is to all loop order, all orders in perturbation theory. And if you have some loop corrections, then they might give you something like log of omega s, but they'll never hurt this omega s to the 0 piece.
Okay.
So when you mean these loop corrections, are you saying that the soft photon is entering that particular loop, or?
Right, yeah,
Oh, so those things will give you that log terms you're saying.
exactly. Yeah, exactly.
I just want to make sure that, so you're saying that there could be from loops, there's things that are more divergent in between these two that just go like log omega s?
Yes, that's fair game.
Then I'm not sure why I care about this finite piece.
Well, just because it's fixed and protected maybe is why you care.
Yeah, but I mean, there's a log in between, it's not universal, right? I mean, you have 1 over omega, you have something unknown times log omega, and then finite, right? But that something unknown times log omega is divergent, right?
Yeah, that's right. Yeah, so I'm not saying these are the first 2 least divergent
Okay,
pieces, but these are 2 pieces that you know.
Okay.
Yeah.
Thank you.
Maybe the number of these universal particle relays or something, or nothing to do with. So far, it's just spin 1 and spin 2.
I see, yeah, it doesn't, I don't think I've heard this. I mean, for soft scalars and supersymmetric theories, there can be a term that goes like omega s to the power -1 multiplied by some supercharge, not some supercharge, some central charge term. So again, the story is it's still out. All that's really known is that for bosons, you have expansions that go as integer powers, and for fermions, it's half integer.
And one more question before you go
Yeah.
on. If I have a supersymmetric theory, do I get some similar soft theorem for like external gluinos
That's right,
or external gravitinos, and that's where this plus a half is, and it's otherwise the same?
exactly.
This result is valid for v greater than equal to 4?
Yeah.
Like that omega log omega.
Indeed, yeah. This, All the people who have been serious about doing this have done it in d equals 4. Just because it's a lot of Feynman diagrams, it doesn't seem like something you want to do in all dimensions. Or maybe in higher dimensions these go away. I'm not sure about the state of the art. That's also possible. But in d equals 4, they are things one has to worry about. All right, we're finally ready to return to celestial holography. So now we've built up this very general theory of how soft theorems work. And I'm going to return to the point of why we're all here, the celestial amplitudes story. So I'm going to define the following set of operators. These are going to be hatted operators, and their conformal dimension is going to be k. And this conformal dimension is going to be, I'm foreshadowing here, it's going to be an integer for the bosons and a half integer for the fermions. We'll see is actually tied to precisely this reasoning here. Okay, so these hatted conformal primary operators are given by the following. Some limit as the conformal dimension goes to this integer or half integer times the conformal primary operator at this dimension. All right, so immediately alarm bells should be going off in your heads. Adam, you're taking a limit of something that's going to, this term is going to kill it immediately. Well, it turns out that these conformal primary operators on the celestial sphere are actually singular at specific values of their conformal dimension. And it's precisely the values where their conformal dimension is an integer for the bosons and a half integer for the fermions. So essentially what this limit is doing is it's extracting the residue of these operators. And these hatted things are the residue, these non-singular parts of the celestial amplitude.
Sorry, I thought, so you're not using the principal series? What is this? What is the complete set of O deltas that you have?
Yeah,
Because it's not 1 plus I lambda anymore.
that's right.
So what is it?
In CCFT, the principal series gives you a complete basis, but it's often the case in which you analytically continue to all conformal dimensions in the complex universe.
Isn't that then an overcomplete basis, and I have to worry about?
That's right. Yes.
Transform back.
So in principle, you can write one in terms of the other, but it's much easier to see what happens when these go to integers than it is to look at special integrals of the complete basis. What are they doing? To reconstruct these ones in terms of the principal unitary series. And I think I mentioned yesterday as well, there's some sense in which the integers also are perhaps going to be a complete basis as well. So in this setting, it's pretty natural from that perspective.
No, I can't take this limited. If deltas are only integers, then it doesn't make any sense to it's only defined on the integers, right? Clearly you have some overcomplete basis where you allow for all complex delta or something.
That's right, yeah, and all these are defined via analytic continuation. Yeah, so maybe if you have the principal unitary series, that's enough to analytically continue through the entire complex plane, and then you can feel free to do this. Yeah, you can analytically continue something from a line, that's enough.
So here you are defining the soft limit just looking at the pole structure. This data was.
Yeah, exactly. So this is actually going to be called the conformally soft limit for reasons that we'll see in a moment. All right. Now let's see what happens when I put this O hat K inside a scattering amplitude. I'm sorry, a celestial amplitude, not a momentum space scattering amplitude. Yeah. So I have some celestial amplitude. Yep, please.
Instead of which naturally does this makes you directly to a hat instead of median transform thing.
Oh, where you integrate these to do the inverse Bell transform?
From the boost eigenstates, usually momentum eigenstates to the boost eigenstate.
Oh, good.
And you did a median transform.
Yep.
Is there a kernel which naturally picks out these?
Indeed. Yeah. So it'll look something like, well, something like this.
Yeah, this was the net.
But you take the rest of it.
So this is related to what you were saying yesterday, but maybe delta only for integers can be complete basis. You just,
That's right. Cool. And later today, maybe tomorrow, if we get to it, I'll talk about conformal primary wave functions. And these conformal primary wave functions often blow up when delta is an integer. So this is taking care of some of that pathology, but we'll see the structure again later, and I think it'll be a bit clearer from that perspective. All right, so we have some celestial amplitude, which is just some conformally covariant correlation function. We put in some random conformal primary operators, and we also put in this O hat. So what is this equal to? Well, I'm just going to use this definition of what O hat is for a moment. So I'm going to extend the conformal dimension to K. And it's equal to the Mount transform of the momentum space amplitude. So I do the Mount transform on all the external legs. So to derive this equation, I've used this definition for what the hatted operators are. And I've also used the definition, literally what the celestial amplitude is in terms of the momentum space amplitude. So this step here is pretty straightforward, okay? The next step is similarly straightforward. I'm just gonna use this soft theorem for the AJ particle to rewrite the scattering amplitude as the soft term associated to J times the scattering amplitude without the J particle. Okay, so this is also immediate. I get all the same stuff here. And now I just have Sj acting on now the end particle scattering amplitude. Good, okay. The next thing we need is the following lemma, which is given to us by our friends in the math department, these analysis people. And the lemma is that limit as epsilon goes to 0 of epsilon over 2 x to the epsilon minus 1 is just delta x. And this holds in a distributional sense. Okay, so I'm not going to tell you how this is derived, but it's true in a distributional sense. And we see that this thing here, we identify this as epsilon. So this is the thing that's going to 0, epsilon's going to 0. And then we rewrite delta in terms of K and epsilon. Okay, so this is what we're free to do. And then when we take this limit, we just get a delta function, which allows us to evaluate the Mount transform of the soft energy immediately. Okay, so I'm not going to go through all the algebra. It's a few steps, but I don't want to do it on the board. And the upshot is that you pick up the following. Okay. So essentially, I've just used this distributional identity to perform this integral. And what I find is that I pick up the sub-leading soft theorem at the minus K order times the Mount transform of the momentum space amplitude. And we recognize that this object down here is just a celestial amplitude. So this is O1 to O1, the celestial amplitude here. Okay, so let me just write somewhere else, let me summarize this main equation. And this main equation is called the conformally soft theorem. Okay. So the conformally soft theorem relates the scattering amplitude with this hatted operator to a celestial amplitude without the hatted operator. And how they're related is via this soft theorem at the kth order acting on the celestial amplitude of n particles. Okay, so this is the big result. Okay. So again, just to summarize some of the big takeaways, is that celestial amplitudes have poles often when their conformal dimensions go to integers or half integers. And what this O hat is doing is we're extracting the residues, these poles. And in fact, the residue of the poles, it picks out the soft theorem acting on the rest of the celestial amplitude. Okay. Moreover, these are dimension K conformal primary operators just by their definition. I'm taking the limit of something that goes to conformal dimension K. So these things are dimension K conformal primary operators. And this dimension K tells you what order in the soft expansion. What order in the soft expansion are you getting acting on the celestial amplitude? So as I go to higher conformal dimensions, I go to more singular terms in the soft expansion acting on the celestial amplitude. And these are called conformally soft theorems because they're related to soft theorems in this nice way. Okay. Next, yeah, please. So it's a great question. This one's an open question. Yeah, sorry. This is a young field. It's like unknown. It's not even me, just not knowing the literature.
We don't even know if it's like multiple software, or whatever.
Yeah, it's a little uncertain.
All this is for one software.
Yeah, good. I mean, there's some work on double soft theorems, consecutive double soft theorems, the order in which you take soft theorems. Sometimes taking soft theorems in different orders, they don't always commute. For example, in the non-abelian case, you know, you get structure constants that appear, things like this. And this is all still, this is still being worked on. This is still like open territory.
Even in one soft hold on, with one soft particle, you get this block of makers and transcripts in this way. So
That's right. Well, yeah, those haven't been studied. Also, double soft theorems haven't been studied. It kind of becomes an order of limits issue. This is still, that's kind of the frontier of the field.
Can you explain the definition once more? So that like fast, no, just right hand side, fast diffusion of this overlap. Yeah.
Oh, this year?
Yeah, so first you take a million transform and then what are you doing?
Yeah, then I just take the limit where the conformal dimension goes to some integer. I'm multiplying it by something that looks like it's going to 0.
Sorry, what happens to the delta minus k in that second line, that second equality? How does that go away?
Yeah, this is
Oh,
this is here. Yeah, the limit as delta goes to k is the limit of epsilon goes to 0, where epsilon is delta minus k. Yeah, good.
Actually, I don't know why I somehow feel that that is not probably necessary because here you are inserting that series expansion, right? For the Sj.
Yeah.
And so you will have a term which is omega to the power minus k times Sj of minus k.
Yeah.
Right. And if you do a contour integration or use a contour of omega s cleverly, that will do that picking up for you without this lemma. Right?
That's right. Yeah. Another way that, so this is related to one of the questions we talked about yesterday, where it's what is the contour of integration? Is it 0 to infinity or perhaps something else? Often one writes a contour of integration just to be centered around 0, and one works in the complex omega plane. And when one does this, this is kind of naturally very similar to what you're talking about. And this is a very useful formalism to define these conformally soft theorems. So you'll also see this in the literature. But formally, they're equivalent. You could use the infinite contour in this lemma, or you could use this closed contour.
I'm still confused about the Kill's question, right? I mean, we just said that if I do some actual Feynman diagram calculation, the 2 loops, I can see that, oops, I try to have a soft thing and then there's a bunch of logs.
Yep.
So is this gonna be a breakdown in the sense that like you have logs and so your contour is
Oh.
not on one surface? I mean, what happens?
Oh, no, so that's fine. So if you put a log in here. Well, then this is just gonna go to 0 because this is an epsilon thing. So whatever integral you get, pick your favorite contour prescription, you're multiplying it by 0. The only time that you don't get 0 is when you have precisely something like this. And if there's a log x, it's obvious, this thing's going to 0.
So, okay, so this statement is what, that you precisely, this is only good for picking out integer powers of omega. You have no idea how to extract the omega log omega terms, is that right?
Yeah, from the perspective of celestial amplitudes, yeah, this is definitely the frontier, yeah.
Have people thought about how to get logarithmic terms?
They have, though I haven't seen too much, or much of any. I've seen, but not too much. It's a very fair question, though. Okay, so now we're going to talk about soft theorems as word identities and discuss asymptotic symmetries. I'm going to circle back to this idea. Right. All right. So let's just consider for a simple example, the case of the delta equals 1 conformally soft photon theorem. Okay. So the upshot is that you have the following celestial amplitude. So where you have this added photon operator at conformal dimension delta equals 1, and then you have these other operators appearing in your celestial amplitude. Now the conformally soft photon theorem at delta equals 1 follows from the leading soft photon theorem in momentum space. Remember how I said that the dimension of these deltas tie you to what order in the soft expansion you get? Well, at dimension delta equals 1, you get s to the -1 power, because positive k here goes to negative k here. And s to the -1 power is the thing that scales like omega s to the -1 by definition. Okay, so the leading soft photon theorem is given by the delta equals 1 conformally soft photon theorem. And you'll recognize this expression I'm about to write in a second. So this is literally just the leading soft photon theorem where I've stripped off this omega s dependence by putting a hat on PS. Okay, just as in the sense of that equation over here. Great. Next up, I'm going to define two operators on the celestial sphere. The first is this J operator.
Sorry, I just want to clarify. If you look at delta equal to 2, that object will be 0.
Good. Yes.
I see.
Yeah.
So there is no delta equal to 2 operator for photon of amplitude.
Integration is 0. There might be some non-universal terms.
No, so delta equals 2 goes to the s to the omega s to the -2 power, of which there is none, because omega s to the -1 is the most singular thing that you can have. So this basically just means that there isn't a pole in the scattering amplitude at delta equals 2. So when you try and extract a residue of something that isn't singular, you get nothing. Yeah. So I'm going to define this J operator as the conformally soft at delta equals 1. This is going to be the positive helicity photon in the bulk, which is to say this operator has spin +1 on the boundary. Okay. And I'm going to define J bar analogously. Where this is √2 times the hatted photon operator with minus helicity in the bulk, which is to say spin -1 on the boundary. Okay. So yesterday we talked about how to relate spin and conformal dimension to these H and H bar conformal weights. So let me just do that exercise here. Here we have conformal dimension 1, spin 1, which means that H equals 1, H bar equals 0. And here we have conformal dimension 1, spin minus 1, which is to say H equals 0, H bar equals 1. Okay. So for those of you familiar with 2D CFT, these things are pretty special objects in 2D CFT. Some operator with H equals 1 and H bar equals 0. This is a conserved current in a 2D CFT. So something that looks like this looks like a conserved current in the 2D CFT. And in CCFT, we'll find that these objects again behave as conserved currents.
The J bar is a function of Z, not Z bar.
Oh, very good. Yeah, very good. So we find that when we stick these things into celestial amplitudes, we have the following relations. All right, so you might be sketched out. What is this Z minus Zi? Where did this come from? Well, all I've done is I've put in this momentum parameterization here in terms of Z and Z bar. And there's a similar way to parameterize the polarization vectors. Okay, so all I've done is a little bit of algebra. And with that bit of algebra, you can get from this expression to something that looks like this. Okay, and this is very suggestive from 2D CFT if you've seen things like this before. And similarly, for J bar, Z bar, when you insert this into a celestial amplitude, you just get the same things, but replace Z with Z bar and Zi with Z bar I. So it's totally the same structure. And the upshot here is that the conformally soft photon theorem are U1 currents in the celestial CFT. Okay. And this equation here is the word identity of these U1 currents. Let me give you an aside, some 2D CFT primer in case you've forgotten something like this. What's meant by conserved currents and stuff like this? Well, the idea is that in a 2D CFT, then you have some U1 symmetry, which is generated by the charge Q. Well, what does that mean? If you have an operator in the CFT, which has charge, it means that it enjoys the following commutator with this U1 charge operator. This is just little q, which is the charge of the operator, times the operator. So this is what it means for a CFT to have some U1 charge. Note that in all CFTs, this is a generic CFT statement, that charges are related to conserved currents via contour integration. So for each charge, you can associate a conserved current, which will be weight 1, 0. And you extract the commutator of a charge and an operator by looking at the contour integral of the conserved current and that operator. So this is just the general 2D CFT expression. This is what the commutator physically means. Okay. And the upshot is that if you want to have precisely this expression here, then it implies that the JZ OZZ bar OPE is the following form. It just looks like Z minus ZI times Q, the charge here. So this is what it means to have a charged operator. It means it has the following OPE with the U1 current, which generates the charge. Okay. Now, if we look back at this expression, it's very reminiscent of what we have here. And indeed, this is just the word identity for some current. So if there's many charged operators which appear in some conformal correlation function, then the upshot is that you just sum over all the operators that appear times this factor, which is dictated by the OPE between the current and the operator. Okay, so this is what I mean by saying that these conformally soft photons are U1 currents in the celestial CFT. So this structure is present here. Okay, great.
Sorry, can you, just for clarity, can you just demonstrate how epsilon naught P2 by, sorry, epsilon naught Pi, that soft factor?
Yep.
Becomes that 1 by z minus z, right?
Sure, yeah, this is a bit of algebra, so how about I'll tell you some of the steps, but not do the algebra. Okay, so there are two polarization vectors, one for positive helicity photons in the bulk, the second for negative helicity photons in the bulk. This structure here is inherited from which polarization you choose. So I've said that J bar is related to the minus thing, and J is related to the plus thing. Okay. So the plus helicity polarization vector is given by this expression, and the minus helicity polarization vector is given by this expression. Okay, so you're taking a derivative with respect to z or a derivative with respect to z bar on this p hat, which is defined here. And now you have all the ingredients that you need to evaluate these dot products. Okay, I've told you what epsilon is. I told you that you can parameterize pi in terms of zi and z bar I. So that's how you're getting these zi's coming in. And then you know the parameterization for ps as well. And you might be worried that when you parameterize pi in terms of this, well, there's extra factors of omega I appearing here, right? I haven't added anything, but they cancel because there's just as many pi's in the numerator as there are in the denominator. Yeah, so this is actually a great exercise to use these kind of ingredients to demonstrate that this is what's going on. Yeah. Cool. All right. So I've done a case for the soft photon theorem and what this means in celestial CFT. Let me make a few more comments before turning to asymptotic symmetry.
Can I just get, so in that this thing you explained now, you have to think of epsilons now as some derivatives.
Right, yeah.
No, it's just a polarization tensor, right? So you have a momentum and it's a photon, so there's two transverse polarizations.
I see you get the.
And he's saying that there's a cute way of writing it, so
Yeah,
that's all.
one I and one minus I. I see that coming, but I'm
Yep.
trying to understand, like, here should I think of them as derivatives acting on the whole correlative?
No, just on the polarization. Yeah, good, exactly right. That's a fair, yes, so let me just clarify that point. When I define epsilon down here in this cute way, it's just some core vector, okay? But other times when I've written, soft theorems or whatever, there are things that act on the scattering amplitude. These partial derivatives which define epsilon are not those things, okay? So this is just some definition of epsilon, but I'm not getting things that act on the scattering amplitude.
And the metric you use to raise and over the Lorentz index is that off diagonal matrix or
the Lorentz index is mostly plus. It's a mostly plus metric. So this is just the diagonal.
Oh, it's just the diagonal, the
Yeah.
usual one.
Right. Yeah. Good.
I just to follow understand. Is there a similarly cute expression for the helicity 2 polarization?
Yes,
tensors?
there is. Great question. Yeah. So it turns out that the helicity 2 polarization vector polarization tensors. So these have two indices.
Yeah.
And they decompose actually into helicity 1 polarization vectors as follows. Yeah, I mean, it's even cuter. So this is true in 4 dimensions. In higher dimensions, the representation theory is, well, it's more difficult, but anyway, yeah, it's nice here. It's very convenient. Okay, so the statement that soft theorems give you ward identities of conserved currents. We've shown this in the U1 case, but this is actually a general feature in CCFT. Which is to say, if you have any massless particle in the bulk, okay, and then you look at its soft theorems and stuff like this, then these will generically be responsible for currents in the CCFT, which tell you about symmetries of the CCFT. For example, if we look at the delta equals 1 conformally soft gluon theorem in the CCFT, then we have some Katz-Moody symmetry, where the algebra of the Katz-Moody symmetry is the same as the gauge. It's the same gauge group in both cases. So if we have some, SU2 gluons, then we have some SU2 Katz-Moody algebra in the CCFT side. Okay. And this is due to some general structure relating soft theorems and asymptotic symmetries, which I will now write. So the Ward identity actually implies the following relationship. So if I take the anti-holomorphic derivative, the one with respect to z bar of this current J, and I insert this in the celestial amplitude, then what do I get? I get I equals 1. I have this sum coming from before, this qi, which is from before. But now I have this 2 pi delta function. And this is due to the fact that the anti-holomorphic derivative hitting something that goes as 1 over z. This is another distributional thing that our friends in the math department have shown us. Okay, so this is some distributional relationship. So we have this expression when we take the anti-holomorphic derivative with respect to J. But now what I'm free to do is I'm free to integrate both sides against some arbitrary function. Okay. So when I integrate the left-hand side against some arbitrary function, I'm going to take up this factor of 1 over 2 pi for convenience. So I integrate it against some function epsilon z bar. You can feel free to choose whatever you'd like. And now you have the celestial amplitude, this top line. The bottom line, however, gives you precisely the following sum. Qi times the function evaluated at the particular points zi, z bar I, where these operators O1 to On live. Okay, so I've singled out precisely certain points in the function corresponding to where these operators O1 to On live on the celestial sphere. And I claim that this here equation actually implies that there are infinitely many conservation laws on scattering amplitudes. And the infinity of conservation laws is due to my freedom to choose epsilon completely arbitrary. Okay, so there are infinitely many relations relating celestial amplitudes in this sense. Let me talk about this infinity of conserved charges back in momentum space language, where it might be perhaps.
Can you explain this infinity of conserved charges again?
Yes, so this will, I'll talk about it in momentum space where it'll be a bit clearer, but the upshot is I can choose this to be whatever I want, and whatever I choose, I get an equality. So this is some conservation law, but I get a new conservation law, whatever I choose.
But why is that a conservation law? Because you're not getting a delta function again.
It's in the sense that it relates amplitudes. It's some, we'll see. Yes, in momentum space, perhaps it's a little clearer, or at least a little more intuitive.
No, but from what I understand is that conservation law means something what you wrote on the top, those delta functions. But if you are doing this integration with this epsilons, you're not getting these delta functions again, right? So why is that a conservation law?
I would say that this is something that's implied by having a conserved current.
Right.
But I guess some conservation law just tells you how to relate amplitudes. So what I could do is I could pull this over to the left-hand side, and then I have some expression involving celestial amplitudes equals 0. In momentum space, we'll define charges associated to these conservation laws, and it'll be even more precise. So if I don't answer your question in 10 minutes, then definitely come back. Okay. So in momentum space, these conformally soft theorems are translated to the following expression. So now it's the anti-holomorphic derivative with respect to epsilon. I have some scattering amplitude with the now photon, which I'm going to take to be soft in momentum space sense, not conformally soft. Okay, so here's what that top line comes to, and the bottom line this gives you a sum from I equals 1 to n of these charges multiplying again the function, which depends on the momenta of these annihilation operators. Okay, so here's what it looks like in momentum space. Now what I'm going to do is I'm going to define the hard and soft operators as follows. So I'm going to define two operators, Q hard and Q soft. Both of them will depend on this arbitrary function epsilon. Okay, so the Q hard acts on an out state as follows. This is by definition. So I'm free to make this definition. I define some operator in quantum field theory, and this is how it acts on asymptotic particle states. Okay, and I define the soft charge as follows. So now it acts on the out state, essentially via the top line. What's going on here? I have some out state, and what the soft charge is doing is to this out state, I add a photon. Okay, but I don't add a photon at a particular value of momentum. I add it at some smeared value of momentum. So I add some smeared cloud of photons, where the smearing depends on this function epsilon that I picked. And then eventually I send the photon to be soft, keeping this omega here. And it looks like, again, this thing is going to 0 because I'm sending omega to 0. But due to the soft photon theorem, in fact, it will be non-zero. And now we turn to this infinitely many conservation laws story. Is I may define the conserved charge Q epsilon just to be the sum of the hard charge and the soft charge. So again, these are all things I'm free to do.
Just keep question that is it related to some going to the Piratha or more like a reference W? When you say infinite many, what the so many people depending on
It'll be infinitely many in the sense that epsilon can be infinitely many.
Yeah. So
Yeah, for the graviton case, you'll see that this is related to W tomorrow.
is it related to W, not
Yeah.
like here. Yesterday you said that you focus on the global, but you
Good.
align to the Piratha.
Yes,
So this is kind of another some people think like an infinite, but this is more like a W.
Right. Good. Okay. Now the upshot is I define the conserved charges like this. And they're conserved in the following sense. That they commute with the S matrix. Okay, so, and this is the sense in which I mean they're conserved charges. This is literally the definition of a conserved charge, something that commutes with the S matrix. And the fact that we have this expression here means that these charges, which I've defined in this way, are conserved in this sense. Okay, so let me give you a little bit of intuition what's going on here. When I choose epsilon to be some constant function 1, what do I get? Well, this bottom soft charge, this is just 0 because I'm taking a derivative with respect to a constant. Okay, so I'm just left with the hard charge. And the conservation law I get here just looks like this. And this is a pretty familiar one. You know, this is literally just conservation of electric charge. So this is a nice thing to see. You know, we've seen it before. Now what we get for a general function epsilon is that Q hard gives you something that looks like a conserved charge state, but it's weighted by the end. Okay, so now it's not just sum of Qi is equal to 0, but sum of epsilon Zi, Z bar I times Qi looks like it's equal to 0. Well, how can this be so? Because I can choose my arbitrary function epsilon such that it's 0 on all these Zi's except for 1. So now it looks like you would get something like Qi just for a single I times An is equal to 0. And this would be bad because this would mean that Qi is equal to 0 or An is equal to 0. Okay. But in fact, when you choose such a non-trivial epsilon, you don't just get the hard charge only. This is compensated by the soft charge as well. So indeed, the conservation law that you get is something like an angle-dependent conservation law, where you smear against these soft photons so as to ensure that indeed you have conservation. Okay. Now, this is related to the asymptotic symmetry story. Perhaps it's best if I talk about the asymptotic symmetry story, and then tomorrow I talk about the stress energy tensor just for time purposes. Okay, but that'll be the first thing tomorrow, so. Good. Okay.
Sorry. So this Q epsilon, when it acts on the in state, annihilate.
They're defined on the in-states almost via crossing symmetry, kind of in a trivial way. So if I want to define them on the in-state, well, this one is literally unchanged, and now this one adds another photon to the in-state, and there might be an extra minus sign here. But, yeah.
So if I take some other non-constant epsilon, so it's some identity, is it something that we already knew?
No, these are totally new.
What are they?
Yeah, they were discovered in the case of gravity in the 1960s by Bondi, Vanderberg, Messner, and Sachs. And in the gravity case, they're related to so-called asymptotic symmetry. So symmetries of asymptotically flat space-time. In the electromagnetism case, these were discovered 10 years ago by Strominger and friends, and they're called large gauge transformations. So what's meant by a large gauge transformation? I'm going to draw our favorite Penrose diagram again. And we're going to let this epsilon, as a function of the space-time coordinate, be some U1 gauge parameter. So specifically, if we have some U1 gauge field, we consider the following gauge transformation. Okay. Now, usually when we think of gauge transformations, we think of them falling off at the boundary. So whenever they get to the boundary, they're assumed to die off. They're assumed to be identically equal to 0. Well, a large gauge transformation is one that does not go to 0 on the boundary. So specifically, Spry at the boundary is some function of z and z bar. Okay, so this is, in fact, it can also be a function of u, but this u information is redundant. So ultimately, it's just a function of z and z bar. And what is this function of z and z bar? Well, I've said that these are large gauge transformations. And normally when you think of gauge symmetry, you're supposed to quotient out by these. But indeed, you only quotient out by small gauge transformations. That is to say, the things that are trivial on the boundary. Large gauge transformations are bona fide symmetries of your theory. And in this sense, to each symmetry, they have a conserved charge. And what is the conserved charge? Well, the conserved charge associated to this large gauge transformation, which goes to this function on the boundary, is precisely this, where I choose the exact same epsilon. Okay, so that's the story of asymptotic symmetries, but we see it re-derived very cleanly in the celestial holography framework. The way Strominger and friends did it in 2016 is they actually wrote down what these conserved charges are in terms of bulk field variables. So they wrote down expressions like this in terms of F mu nu and stuff like this, but they were rather complicated expressions. And we get the whole story of asymptotic symmetries in the celestial holography framework just by noting that there is a conserved current that lives on the boundary. All right, so I think that's maybe all the time I have for today, unless there are some questions.
Can you explain what is a large gauge transformation?
Good. Yeah, so there's been two notions for large gauge transformations which have appeared in the literature, which are not the same. So it's a point of caution. Some communities, when they refer to large gauge transformations, they're talking about things with winding, things that are topologically not connected to the identity, okay? What I'm talking about here, when I say large, is just things which don't die off at the conformal boundary. So they asymptote to some non-trivial thing. For example, in the U1 case, one doesn't frequently think of it, but if you choose epsilon to just be some constant 1, then this is kind of the global part of the U1 gauge group. And this you've seen before. This is what this is what gives things charge in the electromagnetism case. Okay, so, you know, this is something that you shouldn't quotient out by, obviously, right? Like in electromagnetism, if you choose this gauge function, then this is responsible for telling you that things have charge. So you shouldn't quotient out by this. And similarly, you shouldn't quotient out by anything that asymptotes to something non-trivial.
I have one question about this expression for the soft charge.
Yeah.
So there it's like the anti-holographic derivative. But if I start from the beginning by using just the holographic derivative, is it?
Good, yeah. Yeah, so you can do the same story for holomorphic derivatives. The ones for holomorphic derivatives will be related to minus holistic photons.
I can see more realistic.
Good, yeah.
And it is only photon, that there is no gravity.
Good. Yeah, so in the gravity case, turns out that the leading soft graviton theorem will give you something that looks like conservation of energy momentum at every angle. When you also have this soft graviton cloud included. So it looks like you have conservation of energy and momentum at every angle. This is your leading soft graviton theorem. The subleading soft graviton theorem is what dictates the is what gives you the stress energy tensor in your celestial CFT. So that'll be our starting point for tomorrow.
My question is, so here, this QS is only related to soft photon, nothing to do with this.
Yeah, exactly. But you can define a soft charge for gravity analogously.
The reason why I already confused is maybe it must be my misunderstanding, because here you said it relates to W symmetry. Then usually part of W symmetry I expected enough for like
So in the gravity case, it's related to W symmetry. In the gauge theory case, it's related to these asymptotic symmetries. Yeah, sorry, that was too quick probably.
So for the Duino case, are there also higher binding charges and so on?
Yeah, so in principle, if you knew what the soft expansion was to a particular order, then you would find an operator which has an integral H. Yeah.
What I mean is for the large case transformations.
Yeah.
The higher proportionally non-trivial large case transformations for the.
Oh, I see. Yeah, no, that's a different story. Yeah, that's a different story. Yeah. Yeah, all these large gauge transformations, let me recall, these are supposed to be smoothly connected to the identity.
Non-trivial ones are
not, this is not the usual sense. Let me rack my brain though.
because you distinguish between these non-trivial large gauge transformations and just non-vanishing gauge transformations. Right?
Yeah, the usual or the large gauge transformations in this other sense I was talking about, they're often studied in Euclidean space-time. So this makes it a little bit of a difficulty to translate between the two.
You just almost said it's sphere, right?
So
you don't have.
Yeah, I guess I'm saying that the bulk is Lorentzian. So this has something to do with the topology of R4, and you look at, various, the SU2 gauge group can have some winding, and on the boundary it doesn't look like the identity or something like this. But this has to do with homotopy groups of S3 and blah blah blah, and it's quite a story.
But I thought since you're talking just about epsilons which are defined on the sphere.
Yeah.
We just talk about the.
Yeah, I mean, in principle, you can choose whatever epsilon you'd like. And I'm not saying that some are connected to large gauge transformations in one sense. I'm not saying that they won't be connected in that sense. But this is perhaps even like a broader class of things. You can choose whatever you want here.
It's maybe worth just commenting, because maybe some people in the audience are much more familiar with this notion of kind of large diffs, large gauge transformations in the context of ADS, where it's much more familiar.
Right.
And there everything is really easy because you have a time-like boundary. And so it is just global symmetry transformations on your boundary filter space. The point is that it's morally it is the same thing, right? You have something that locally looks like a gauge transformation, but it's not a null direction with respect to a symplectic structure.
Good.
And so it isn't a pure gauge mode the way that something that dies off is.
Yes, that's 100% right.
So like, I mean, if you've ever thought about ADS3, you've spent time thinking about this, right? Yes.
Yeah, no, that's a great way to put it.
This can be somehow related to. Yes,
People have begun studying soft theorems and asymptotic symmetries in the CFT, but that's a very underdeveloped subject, I'd say. So the jury's still out. Yeah. It seems like there's some edge modes for photons and stuff like this in DSCFT. And this looks like asymptotic symmetries. But the structure hasn't been totally formalized like this.
Maybe you can have, or you will cover tomorrow, but if when you say W1 plus infinity, one is from the photon or one is just
No.
graviton?
Yeah, one's from the graviton.
But the one is usually spin one, later spin one.
Yeah,
right?
so this will be,
In graviton, you have spin one, some.
yeah. Well, roughly, yes. Let's see. So they'll all be spin 2, but it's because the spin. Good. So the W algebra has a notion of spin, but the spin of what will ultimately become the W algebra isn't the same as the spin of the things that are in the bulk. So you'll have spin 1, spin 2, spin 3, spin of the W algebra, and they're somehow related to the conformal dimensions of the operators on the CCFT, but the spin in the W algebra isn't just H minus H bar. It's something else. Yeah.
So when you do this, maybe if you pick for the graviton case, you would have some kind of in CCFT point of view, you have some spin 1. It's not the work spin 1, but some K for 1.
Yes.
Right?
Yeah, with respect to like the Virasoro algebra, which is a subalgebra of W. And the Virasoro algebra, which is a subalgebra of W, will end up not being the same as the Virasoro algebra that you get from the subleading soft graviton theorem. Yeah.
Then why not K for 0? It's will be like here is simply you have K for 0 and K for K for 1 and K for 2. You take a limit that was K.
Yeah.
K then K. So we have K for 2 and 1. And from K for 1 to this W 1 plus infinity, and that 1 is 1 in the CCFT.
Yeah, so it turns out in the gravity case, you need all the K's together to get W. So if you get some subalgebra of W just by looking at a particular choice of K, but to get the full W, it comes when you consider all the K equals 2, 1, 0, minus 1, minus 2, so on.
You already have to choose the K equals 0.
Yeah, so you need this here, but it's like the full algebra of all these objects together. We're going to look at various commutators of all these objects amongst themselves.
In one case, it does not.
Yeah, in the spin 1 case, you don't get a W algebra, rather you get an S algebra. Yeah, I don't know if you know the S algebra. It looks something like. So for a non-abelian theory, S algebras are only defined, or they're only non-trivial for a non-abelian theory with some structure constants FABC. Here are the generators of the S algebra, and this is the expression for the S algebra.
K for 2 plus 1 the energy and the CCFT, if I understand correctly. The K for 2 operator is the energy.
Oh, sorry, no, the K equals 0 one does.
Yeah.
The K equals 2 one actually gives a trivial soft theorem, but somehow it's useful in the story of W.
K equals 0 gives the energy.
Yeah.
do not recall, you're saying that there's a problem with that epsilon chosen to be one everywhere. What problem does it lead to?
Oh, so in the usual, maybe I was a little fast with this. In the usual QED story, maybe the way that you were taught QED when you first learned about electromagnetism, you're told that all gauge transformations are trivial, they should be quotiented out. Even in the most basic case, you know that this is not true. Because if I choose some gauge transformation, which is just equal to 1 everywhere, this is actually a physical thing. This shouldn't be quotiented out. This is, for example, this is responsible for the U1 global symmetry. So if you have some charge field, e to the IQ, phi, you know, this is, in principle, there's an epsilon here, but I choose epsilon to be equal to 1. So choosing epsilon to be equal to 1 is related to the global U1 symmetry. Is that?
Okay.
So we already know from basic QED that you shouldn't quotient out everything that looks like a gauge transformation. In fact, the ones that you shouldn't quotient out are precisely the ones which are non-trivial on the boundary. And this simple example of epsilon equals to 1 everywhere is one such example where you have something that's non-trivial on the boundary.
Questions? Okay, we can continue discussion. Also, thanks to